SwayamPrabha. Digital India. Educated India.
Welcome to this lecture of design practice for intelligent system. This time I am going to talk about something new to you, and that something new literally means something new, which means that suppose you followed the axiomatic design, suppose you have a design with you and then you want to take a patent out of it, right, because you want to really protect the intellectual property of your hard work, fairly reasonable, right. How do you really know that this is really novel? It is possible that you have what we call quote unquote reinventing a wheel, right. So, how do I know that something is novel? That question had actually sort of bothered lot of patent officers. Einstein himself also was a patent officer. So, that question bothers the patent officers, and one of these patent officer in Russia in 1940s, his name is Altshuler. He had then figured out that there are certain telltale signs of inventiveness in a patent, and that is what he put in these trees, which is a Russian term, but what it means is that theory of inventive problem solving. This is what we are going to learn together today. Okay. So, we will call it in English then, the trees is also required as tips, and I am going to give you tips that how do you know that your design is truly unique or not. Now, again keep in mind that I had discussed some part of it, that there are generally 6 phases in any new product development, and intelligent products are not away from it. It has to satisfy it. The first is always you have to check with your customer, what does they need. So, the need statement, the design always starts from the need statement and the constraints that also the customers will say. And you remember I also told you the voice of customer and voice of business, you have to hear from the both. The next stage is concept generation, which is what I told you in the last class. Now, after the concepts are generated, you have to select the concepts, and naturally we try to select the concepts which has some uniqueness in it. And then later on in this course, we will look into the embodiment, some product matrices, and then certain techniques called design for manufacturing, design for assembly, and design which is from the failure point of view, it is failure proof, etc. So, let us look into the concept selection time, what is it that will be bothering us. So, one important thing in the concept generation part I told you is that how you are generating the concept, whether you are doing it as an individual, then people use action verbs, checklisting, etc. In a group, people use these techniques called brainstorming, synectics, progressive or sequential, storyboarding, etc. But we have done more directed way of doing it. One of them I have talked about, axiomatic principle. Design catalog is important when it is already available some products, and the next one I am going to see, which you can utilize both for concept generation as well as for concept selection, is the theory of inventive problem solving. So, let us look into it. Well, in the language of Altshuler, no contradiction, no problem, which means the basic tenet of trees is that it is defined by contradictions. Any new design must have some contradictions in it. Now, these contradictions will be initially physical contradiction, and our challenge will be to translate all the physical contradiction to technical contradiction. What is technical contradiction? Well, in the language of engineering, it is called trade-offs, like the desired state can't be reached because something else in the system prevents it. For example, a product gets stronger, but the weight increases. The bandwidth of a system increases, but it requires more power. These are in terms of technical specifications. So, these are technical contradictions. Well, technical contradictions, you can also think of. For example, a vehicle has higher horsepower, but uses more fuel, a contradiction. Electric vehicles need to go long distance between recharging, but the battery weight then gets too high, a contradiction. And many other from your experience, as I will be talking about, please start to think of it, that many other contradictions. Now, suppose you do not go into technical contradictions, at least you will be able to do the physical contradictions. Situations where objective has contradictory opposite requirements. I will give you some very simple examples. When pouring hot filling into chocolate candy shells, the filling should be hot to pour fast, but it should be cold to prevent melting of the chocolate. So, that is something which is a very important contradiction in a hot chocolate fudge. It has to be done in such a way that the fudge is edible. It should not become a simple mesh of things, or it should not become too cold. I will give you another one, that the aircraft should be streamlined so that it can fly very fast, but they should have some protrusions like landing gear and also the wing changes, so that you can maneuver, you can slow down the speed also in the ground. Aircraft should fly fast to go to the destination, but should fly slowly for minimum change in velocity on landing. Same thing is true when we design a highway. Highways should be wide for easy traffic flow, but if it is too wide, people go with a very high velocity, and if there is a collision, they die. So, it should be narrow for low impact on communities. So, you have to solve the contradiction. There are many examples of physical contradiction, like upholstery should be luxurious, but it should be then easy to maintain. A frame should be heavy for structural safety, like my frame of the spec. From the point of view of holding these lenses, have to be heavy enough so that it can hold it. It should not get bent or deformed, but it should be also light, and also it will reduce the cost then, and ease of assembly will be there. So, like that you will see thousands of physical contradictions each and every day, and your job will be to transform all these physical contradictions to technical contradictions. Then only we will be able to use the prism of trees, and trees in Russian is Teroya Reshnia Izobretaleksik Zadach, quite a tongue twister. That is why I said you keep tips in mind, theory of inventive problem solving. Now, there are 39 almost standard features for any technical contradiction to arise. These standard features you have to keep in your mind. First feature is that weight of an object that can move or is moving. Think of a car, weight of the car, a car can move. So, weight of that, a dynamic system is one technical specification. You can have another system in which the thing cannot move, like let us say this pen or this mouse. So, weight of an object that is still or cannot move. Similar thing is true from the dimension point of view. Dimension of an object that can move, we call it as let us call it as dimension m, and dimension static like weight m and weight static. And same thing is true for area m and area static, volume m and volume static. Then there comes speed, and then there comes force, stress or pressure which is over an unit area, shape, then stability, the strength, duration of action of an object that can move or moving. So, again movement, and duration of action, that is still S. Temperature, brightness, energy, again energy has two components M and S. Then power, loss of energy, loss of material, loss of information, loss of time, quantity of matter, reliability, measurement accuracy, manufacturing accuracy, harmful effects on the object and harmful side effects, ease of manufacture, ease of operation, ease of repair, adaptability versus versatility, system complexity, control complexity, degree of automation, productivity. So, these are the 39 generally observed points in which the technical contradictions happen, right. For example, I just tell you one example. Let us say I am thinking of a car. Okay. So, for a car, so the car has some weight. Okay. So, you think of the car. Okay. Now, the weight of the car is one feature that let us say you want to improve. Okay. So, whatever I want to improve, I give a arrow that I am trying to improve it. So, improving the weight means I am trying to make it lightweight, okay, with which I can have a contradiction about it. Well, if I make the car lighter and lighter and lighter, I know that there will be a challenge in manufacturing, because there can be the buckling of the sheets. So, the ease of manufacture is going to have a contradiction. If you have a very thin sheet, you will not be able to manufacture the car so easily. You have to think of different techniques, and then if you want to take care of that, the cost will increase. So, this is just one example that where the number 1, this was number 1 and number 32, they are in contradiction. That is a technical contradiction. Like that, you think of any such technical contradictions, that is the first important thing. Start to think from now itself for any product design you have in mind. If it is intelligent, that is the best, and then what are the contradictions that will come. Invariably, you will come with some features which are improving and some feature which are going to have worsening features in it. Now, what we do in trees typically is that I define my problem in terms of such contradictions, and trees has already found out what are the known solutions to solve this puzzle through trees. And then once you get the hints from trees, you would be able to create your analogous solution, and that will give you your solution. So, this mapping is something that you can do it through trees. So, the first important point is identify your problem, okay? And then operating environment, let us say storing a beverage can, an energized engineered system to contain the beverage is what is your challenge. Operating environment is that cans are stacked for storage purposes. So, it has to have a particular type of shape. Resources include weight of filled cans, internal pressure of can, rigidity of can construction. Primary useful function is to contain the beverage. Harmful effects include cost of materials and producing can and waste of storage space. An ideal result is a can that can support the weight of stacking to human height without damage of the cans or beverage in cans. That is what is typically the driving factor of these, let us say, the Coca-Cola cans. Formulate the problem now in terms of the prism of trees, that is, restate the problem in terms of first physical contradiction, identify the problems that could occur, and then map it in terms of technical contradictions, technical conflicts, and then use the trees matrix for the solution. There are many examples, like in the can problem, like we cannot control the height to which cans will be stacked, the price of raw materials, the can walls must be made thinner to reduce cost, but if we make the walls thinner, it cannot support as a large stacking load, it is going to buckle. The can wall needs to be thinner to lower material cost and thicker to support stacking load weight, a contradiction, and then you can map it in terms of a technical contradiction. Now, using, as I told you, the trees matrix, which I will come at the end, you can search for previously solved problem, like there is a particular principle dimension of a non-moving object versus the thinner like stress, and then this is a standard one. What are the principles that people have used in order to solve the problem? You have to use a contradiction matrix to do it, which I will say towards the end, and the contradiction is between 4 and 11, and what you would see is that there are principles 1, 14 and 35. Keep in mind that the contradiction is between what? Between the thickness of the system, and that is technical contradiction number 4, and versus 11 the stress. If you go a little bit back towards those numbers, you see it is basically dimension of a steel object versus 11, that is the stress or pressure. That was our contradiction, and I told you that 1, 14 and 35 are the principles that people have already used to solve the problem. For example, just I am telling you beforehand, although I am going to go through the principles now. Principle 1 has one that people have already tried for such contradiction, that is, increase the degree of an object segmentation. That means, the wall of the can could be changed from smooth to a corrugated one. If you look at this particular water bottle, precisely that is what they have done. They have made it corrugated, so that even a thin sample can hold the weight. So, that is what is the principle 1, that increase the degree of an object segmentation. Segmentation or modularity, we will very soon we are going to see it. Principle 14 talks about perpendicular angle at which most can leads are welded to the can, and that can be changed to a curve. We will see what is it. And principle 35 tells us that change the composition to a stronger metallic alloy or to a polymer which can sustain the load, but yet it has a low density. So, 1, 14 and 35 thus can be used to solve your problem. Now, that means I have to know what are these principles to begin with. There are 40 such principles. So, we have 39 contradictions, we have one extra principle. Let us look into these principles one by one. Okay. So, there are 40 principles, okay. And I told you that for these Coke can or for any such stacking thing, we have used segmentation, we have used these kind of principle which was 14, right. We have used 14, spheroidality, curvature, increasing the curvature, and we have used, I think, the property of the material is something that we have used. So, either you can use the principle here of the parametric changes or the composite materials, either of them. So, this now let us look into the principles. Principle 1 is that of segmentation, and segmentation talks about dividing an object into independent parts. You look at a good spanner, you will see that it has been thought exactly in this way. There are many independent part of it, okay. And that is one. The other part of segmentation is make an object easy to assemble or disassemble, so that you design it in such a way that you can sort of very quickly open it, or you can very quickly join things together. And the third point is that increase the degree of fragmentation or segmentation. That means, if it is already fragmented, you increase the degree. You see the razor blade that we use, the standard blade versus the Gillette blade, you will see there are so many blades there. So, that means, one after the other actually goes through the same beard to cut it. So, increase the degree of fragmentation. So, that is the principle 1, principle of segmentation or modularity. I always say that two are the greatest beneficiaries of this. One is the computer designed by Microsoft. Before Microsoft's personal computer, there always used to be only huge supercomputers, but Microsoft had successfully segmented the computational power into small pieces. So, the design of personal computer is a good example of modularity. And the second example I always say is of furnitures, that today we have furniture companies in which you can get your furniture in small parts which you can reassemble very quickly. So, that actually improves the business of the furniture and the accessibility of the design. So, that is the significance of principle 1 of segmentation. Principle 2 is taking out, that is, take out an interesting part or property of an object, single out that and throw away the rest of it. For example, many of us go to the shopping malls, but it is air conditioned, but we never get the sound of air conditioning. Why? Because of the technology of something similar to split, that is, the cooling happens at one place, but the noisy compressor is kept somewhere else outside the building. So, that is the principle of taking out. Use the sound of a barking dog without the dog. So, like a burglar alarm or use of a scarecrow. Well, I always also, there are some examples we have given here, but I always also give the example of, let us say, the fruit juice. You extract the juice of a fruit and throw away rest of the things which you do not want to waste your time for, taking out, or the perfumes. You use the, extract the good part of a fragrance and throw away the rest of the flower. So, these are all principle 2 of taking out. Principle 3 talks about local quality. Change an object structure from uniform to non-uniform. Always keep some local quality. For example, you see the very pen I am using has local qualities, because is not entirely uniform. It has a different shape here, so that I can hold it easily. Okay. So, uniform to non-uniform. Change an external environment also, if possible, from uniform to non-uniform, and make each part of an object function in conditions most suitable for its operation. For example, a refrigerator is not cold uniformly everywhere. You have a freezer compartment in the refrigerator, different zones in a combustion system of an engine. So, these are all examples of local quality. Principle 4 talks about asymmetry. Asymmetry is explored in a very wide scale. For example, the greatest example is an aircraft. The aircraft wing, if you look at it, its top and bottom are of different shape, and we call it to be an aerofoil shape. That actually helps the to generate the lift of an aircraft. So, there we are using the principle of asymmetry. Or change the shape of an object to suit external asymmetries, like ergonomic features we add. For example, car steering system compensates for camber in the road. Wing design, already I told you. Turbo machinery design takes account of boundary layer of flows. So, change the shape of an object to suit the external asymmetry. If an object is asymmetrical, increase its degree of asymmetry, and that you can do for aircraft wings, for special connectors, for different types of scales on a ruler. You basically increase the degree of asymmetry. Principle 5 talks about the principle of merging. Bring many features closer together, like identical or similar objects or operations in space, bring them together. For example, multicolor ink cartridge, the same cartridge having multiple colors in it. Bifocal lens spectacles, same lens but having two different, the sort of the focal length. And then double triple glazing or strips of staples. Make objects or operation contiguous or parallel, bring them together in time. Combine harvester or mixers, or pipeline a computer processing system for different stage of calculation, vector processors, Fourier analysis itself. So, operations contiguous or parallel, bring them together in time, parallel processing. Okay. So, this is the example of principle 5, that is what is called merging. Principle 6 talks about universality. Make a part or object perform multiple functions, eliminate the need of other parts. See, for example, I have again this pen, the tip of it actually put some thing here, and the bottom part of it, end of it actually has an eraser in it, which you can use to erase this whole thing. I can erase. So, that means it is having this property of universality in it. So, similarly, a Swiss army knife having multiple functions in one place, grill inside a microwave, radio alarm clock, both radio as well as alarm clock, right? CD used as a storage medium, or bathroom light switch that starts an extractor fan also. So, that is the principle 6 called principle of universality. Principle 7, if I go, that is very important whenever you have restriction of space. It is also known as Russian doll's principle or nested doll. Russian doll is basically a doll inside a doll. So, place one object inside the other. Okay. Plenty of examples you will find out in real life, including a retractable aircraft undercarriage. Place multiple objects inside others, like nested tables, telescope, measuring cups, stacking chairs, many such examples. Make one part, this is interesting, pass dynamically through a cavity in the other, like telescopic car aerial. So, one part goes to the other, or retractable power lead in a vacuum cleaner, or the seat belt retraction mechanism, tape measures, one part of the tape goes inside the other and fold. So, these are all the principle 7, Russian dolls. Principle 8 talks about anti-weight. To compensate for the weight of an object, merge it with other objects that provide lift. So, the kayak with foam floats, right, or aerostatic aeroplane. You are basically using a very lightweight thing, and that is what is the anti-weight. You are using something which compensates. Or to compensate for the weight of an object, make it interact with the environment, for example, aerodynamic or hydrodynamic interactions. Okay. So, many different types of vortex generators, vortex shredding mechanisms, hydrofoils, aerofoils, they are all based on principle 8, either A or B, either of them. Principle 9 talks about preliminary anti-action. So, if it will be necessary to perform an action with both harmful and useful effects, this action should be replaced with anti-action, so that that harmful effect can be controlled. Masking objects before harmful exposure, okay, or predict effects of a signal distortion and take care of it beforehand, or use a buffer solution to prevent harm from extremes of pH. And another possibility is also there, that is called create beforehand stresses in an object, which is called pre-stressing. very much used in today's quickly deployable structural system. Create beforehand stresses in an object that will oppose known undesirable working stress. This is what is called principle 9, preliminary anti-action. I will then come to principle 10, preliminary action. So, this principle talks about that you perform some of the work beforehand, like you pre-paste wallpaper. 3M company is one of the best examples. All the stick sheets are the best example of preliminary action. Self-adhesive stamps. Before this, self-adhesive in the stamp was there, people used to have so many spitting on the stamp. Self-adhesive has taken it out. Holes cut before sheet metal part formed. So, you take some part of the action beforehand, or pre-arrange object, which is also important in the context of design manufacturing system. So, pre-arrange objects such that they can come into action from the most convenient place and without losing time for their delivery. Manufacturing, I said, flow-line design is very important towards that direction. There are many other, like the car jacks and all other manufacturing related issues, does this preliminary action very much. So, thus I have discussed 10 principles with you, and then we have to discuss about 30 more principles and then the application of it. So, let us put an end in our discussion of today's lecture here itself, and thank you. We will continue this in our next lecture.